We have Professor Preeti with us here for the talk, Music Applications of Fourier Analysis. She is a professor at Department of Electrical Engineering, IIT Bombay, and also co-founder and director of Sensible Audio Technologies. She did her B.Tech in IIT Bombay and PhD in University of Florida, after which she was a postdoctoral research associate, University of Illinois at Urbana-Champaign for 2 years, and a visiting researcher for a year at Central Research Laboratory, Speech Communications Group, Hitachi Limited, Tokyo. I respectfully invite her to begin the talk.
Yeah, thank you. And I'd also like to thank the organizers for this opportunity. Really nice being here, looking at a room full of very bright young girls, budding scientists. And I know it's been a long day for you, but this talk, maybe, we won't, see the kind of rigor that you're seeing in your classes, but, it's meant to be a popular talk, and you'll also hear snippets of music. And I'm glad it's coming right after Janvi's really interesting talk, where she raised a lot of questions about science and the public, and does the broader scope of science than we traditionally think about it, because we are going to see some things about how science has been applied also to music, okay, and how almost anything can be studied analytically and with a scientific temper and make you all the richer in terms of the knowledge and the experience it brings. Okay, so this is primarily about how some of the tools that we can use to understand music, and which eventually benefit us in terms of appreciating music, as well as the lot of music technology that we see around us. And there's one very unshakable and important pillar there, and that is Fourier analysis. So what does Fourier analysis bring to your mind, in the sense, what do you associate the name Fourier with at this stage of your college education? Yeah, I think somebody said something. Right, Fourier series. So actually, Fourier was a mathematician, and this Fourier series is something he proposed in connection with heat conduction. So that was the original problem he was working on. Where he postulated that a function can be decomposed into sines and cosines, very simply speaking, correct? It turned out to have much more wide-ranging impact, beyond heat conduction. And one of the areas, other areas, so there are lots of areas impacted by this kind of theory, and one of those areas is acoustics. So when we are talking about music, we are talking more of about sound and the signal, because that's exactly how we consume music, right? We consume music by listening to it, right? So that's something that I'm going to try to connect in terms of what you understand as a theory and what it really tells us about the properties of this function that or this sound signal that we call music. Okay, so let's start by talking about sound. So sound is generated by a vibrating object, right? So you strike something and you hear a sound, that's because something is vibrating. And when that object vibrates, it creates this motion in the air between the vibrating object, and that motion travels by what we call a longitudinal transmission of some compression and rarefaction. There has to be a medium, correct? And air is the medium for us typically, and it reaches our ears, right? And how do we perceive the sound? Because of a eardrum vibrates, and then there is a whole chain of events which finally translates into us feeling a certain sensation, in our brain, in terms of being able to say something about sound. The sound turns into a meaning for us because of the processing that occurs between the vibration of the eardrum and our brains, right? Now, of course, we have devices such as microphones. So something that I'm using now is a microphone. A microphone is a vibrating membrane which converts the mechanical longitudinal air motion or vibration into an electrical signal, correct? So it could be a moving coil in a magnetic field, or something that actually essentially picks up the same movement and produces an electrical waveform that pretty much follows all the perturbations in terms of the changes of pressure, and it makes it available to us in terms of voltages or currents, right? So we can actually handle these signals, we can record them, correct? So suddenly by changing something mechanical into an electrical form, it opens up a whole new world of possibilities on what all we can do with that sound, right? Okay, so here we see a very simple sound. What kind of waveform is this? It's a sinusoid, right? Or a sine function. So it's just telling us that it's pressure versus time, and we can see it. For example, a tuning fork is some kind of a device that you're very familiar with that is, sort of very commonly used to produce what we call our pure tones, right? So we produce a single sine wave which has one component, one frequency, and we call that a sine or a sinusoid. A tuning fork is one instrument that generates such a pure sine wave. So its construction and the way it is struck and all that somehow leads to its having only a single resonance, and that is a pure sine wave. Okay. So if we were to listen to this sound of a particular tuning fork which is tuned to 440 hertz, this is what it sounds like. Right? It was struck once. So you heard that sound. So that was what a sinusoid of 440 hertz sounds like. Okay, so let's look at another more interesting sound. Okay, so what did this sound like? Yeah, it sounded like a ship horn, or maybe even, yeah, it could even be a very large wind instrument. Of course, that's probably what a ship horn is. And what do we see here? We see this function of time. So we earlier saw a sinusoid function of time, and now we have a different function of time here, right? But there's something common between the two, and that is they're both periodic, right? This is perfectly periodic. It has a rather peculiar waveform shape, right? But it is periodic. And it turns out musical sounds are periodic, okay? Except for certain sounds. Can you guess what musical sounds may not be periodic? What we traditionally call musical sounds? Yeah, a bell. Okay, so maybe we'll take that question up later. Yeah, there are certain sounds, particularly percussive sounds, which are struck only once and decay very quickly, which are not periodic. Okay? But largely, musical sounds are periodic, and that's why, we actually find that Fourier analysis, which actually talks about the decomposition of any function into sines and cosines, and in particular, when we talk about periodic signals, we have something even more definite, and that is that we get specific components, right? So we have any periodic function can be decomposed into a sum of sines and cosines or sinusoids. And it turns out that these sinusoids are, and their properties, in a sense, their frequencies, their amplitudes and phases actually tell us something about the nature of the sound itself in terms of how we perceive it, but they also tell us something about the source of the sound. Okay? So that's why we are very interested in looking at the Fourier series decomposition of acoustic signals, and in particular signals which are periodic, which I said most musical signals fall, in which category most musical signals fall. Okay, so what does it tell us about acoustic signals in particular? It tells us something about the properties of the source of sound itself. For example, what are the resonances? Like we saw the tuning fork example. When we look at the sinusoid produced and measure its frequencies, it tells us the resonance of that particular tuning fork, right? And what is the description that we have for that sound? We often talk of a sound in terms of a periodic sound, especially in terms of its pitch. Okay? So if you had two different tuning forks tuned to different frequencies, you would be able to say which one is the higher pitch one, right? And where does the pitch appear in that waveform of the sinusoid? Where is, in terms of the period of vibration, right? Or the number of cycles per second. So when we said that was a 440 hertz sinusoid, we meant that there are 440 cycles per second in that function of time, right? Or its period is 1/440th of a second to complete a single cycle. And that relates to our perception of pitch. Okay, so this was a pure tone signal. And if we have to show visually what its Fourier analysis is, then we would show it by drawing a single component at the frequency location. Okay, so now this happens to be a sinusoid of frequency 200 hertz, and that's why we've drawn a single, a vertical line there to indicate that it has a single component. Its amplitude is roughly 0.8, whatever those units are, but its frequency is 200 hertz. Okay? And the reason for drawing a single component there is because a sinusoid is that basic function that we are talking about, and all we are doing is decomposing this signal into its sines and cosines, and that's giving us that single sinusoid. So that was what you also heard before. Okay, so when you look at the second signal, which was the one that sounded like a ship horn, and if we do the Fourier decomposition of that signal, you suddenly begin to see a lot of different components, right? And these components are not arbitrarily placed in frequency. They happen to have a relationship with each other. They are all multiples of a basic frequency that we call the fundamental frequency. Okay. So what we have in the case of this is essentially a Fourier series decomposition. So we are representing a periodic waveform in terms of its fundamental frequency, which is the first frequency component, and its overtones or its harmonics. Okay. So what are the frequency components here? We have 200, 400, 600, and so on. And they all have different amplitudes, and they all combine so that if we added sinusoids of these amplitudes together, again, we would actually be getting this periodic signal. Okay, now this shows how this relates to sound production. Okay, so here we have a string that has been plucked. And because of the nature of the vibration of the string and the constraints that we see here in terms of having displacement nodes at the two ends, the resonant modes of the string correspond to all of those shown over here, right? So we have a fundamental, then we have something that is twice the frequency, 3 times the frequency, and so on. And if we add these all up, assuming that we pluck the string in a manner, so the string can be plucked in many manners depending on where it is plucked. It does not have to be plucked in the middle. It will give rise to a vibration of a period given by this fundamental frequency, but it will also excite all these other modes, and eventually you get a certain waveform corresponding to the plucking of the string. And if you were to do a Fourier analysis of that, you end up seeing again multiple tones, and the frequency components are the fundamental and the multiples of the fundamental, as we see over here. Okay, and to change the pitch of the string, essentially we would be changing the length of the string. If you keep the tension and the material the same, you essentially can change pitch by changing the length of the string. And that's exactly how a lot of musical instruments work. For example, when you pluck a guitar string, you get a certain note or a certain pitch. But should you change, and how would you change the length of the guitar string? Typically by placing your finger on the fret at a particular location to shorten the string, and that would give rise to a different length. And with the different length, you end up getting a different fundamental frequency of vibration, right? Okay, so let's talk a little bit about what we really perceive when we combine. So essentially, we can generate a limitless combination of sounds by putting together different frequency components. And as we said, sounds actually sound musical only when the components are related to each other by this harmonic relationship. Okay? But even within that, we get to choose where those components lie, assuming that they all have a harmonic relationship, but what is the fundamental frequency that we choose? And also, what are the amplitudes that we choose for the different components? Okay? And depending on that, you get a completely different waveform. So what are these waveforms? So I'm going to have, we see here 3 sinusoids which are related to it in the relationship of being multiple. So we have a fundamental frequency, twice the fundamental frequency, and 3 times the fundamental frequency. This happens to be a 300 hertz component, a 600 hertz component, and a 900 hertz component. And then we have the combination of components in terms of adding the first 2 and then adding all 3. Okay, so we listen to them and notice, listen for the quality of the sound, and let's see if we can relate our understanding of or knowledge of the components of the sound to what we perceive as the quality of the sound. Okay, in terms of which are the ones that are similar and which are different and how they are different. Okay, so I'm just playing the first component, 300 hertz component. So what would you name as the difference between the three sounds? Pitch, right? So they were getting successively higher in pitch, right? Okay, so now let's look at this one, which is the sum of the first two components, and each of the components had a different pitch, remember? Okay, so is there anything that you can say about the similarity of these last two sounds to the first three? Okay, so you understand how these sounds are obtained by adding these, right? So if you just do this actual addition of these waveforms, for every point in time, just superpose these, you're going to get the fourth one. And if you superpose all three, you get the fifth one. Okay, so let's ask the question as to, in terms of pitch, for example, which of the sounds does this one match in terms of, it has three components, but pitch wise, which one of its three components does it match? Okay, so I'm just going to play this. So which one is it most similar to? The first one, right? Okay, and that's also evident if you look at one more property of the waveform, and that this waveform is periodic, but the periodicity of this waveform actually matches the first one, right? So the period is this, and in fact, it is the period that is giving rise to the sensation of pitch. So if I talk about cycles per second or the fundamental frequency, then the fundamental frequency of the fourth waveform is actually identical to the first one, right? And that explains, that is that similarity which actually relates to the sensation of pitch. Okay, and what about the fifth waveform? What do we expect the fifth waveform to sound like in terms of pitch? Also like 1, right? But they were different, right? So could you tell the difference between the fourth and the fifth one? Right, they're different, but it's hard to describe the difference in words, right? But the difference in the quality of the sound, or what we call the timbre of the sound, it actually arises from the fact that they have different frequency components, and of course their waveforms are also different. Okay, okay, so I'll have more to say about this as Okay, so let's talk about, we talked about pitch, so let's talk about timbre or tone quality of color. So timbre refers to this quality of being able to differentiate sounds which are similar in pitch and also in amplitude or loudness, but still sound different. So then we tend to attribute that different sensation to the fact that the sounds have a different timbre, okay? And the timbre arises because of the relative amplitude. So if you have two sounds with the same pitch, you would have these frequency components at the same location, but if you were to change the amplitudes of the components, you would get a sound with unchanged pitch, but with different timbre. Okay? So that is what we saw in the previous case, that we still had components at 300 Hz, 900 Hz, 300, 600, 900, but we changed the components, we made some 0 or we make some small. We are actually going to hear a difference, which is not a difference in pitch, because the fundamental frequency or the period is still unchanged, but it is these spectral amplitudes, or the Fourier coefficient amplitudes, the Fourier series coefficient amplitudes that are different, that are giving rise to that changed quality. Okay? So this also has a special name. It's called the spectral envelope. So if you were to just join all of these and sketch a envelope around these components, we would call it the spectral envelope of the sound, and this particular timbre that we hear is linked to the shape of that spectral envelope. Okay, so that was about sounds like that, but in the real world, actually, we have far more complex sounds. We've only been listening to very simple tones. So for example, as we speak, we are actually creating a number of sounds, and we are mentally breaking up the speech that is falling on our ears into basic sounds. For example, if I say the word the but, I'm actually uttering 3 sounds, b, and t, And then, each of the sounds are being analyzed for, to associate them with whatever meaning we associate with those particular sounds, having learned the sounds of the language. Similarly, in music, we have different notes playing, and each of them has different properties, right? Okay, so here is what we might call a very simple, signal of music, where we are actually going to hear a series of notes, and all of the notes have different pitches, and that's what makes the music interesting. It sometimes goes up and sometimes comes down. But what is important to note in music is comprised of a series of discrete pitches. Okay, so the pitches themselves take on certain, those fundamental frequencies itself are drawn from a discrete set. For example, on a keyboard, we have, each note conveying a different pitch, and all music is being constructed from that closed set of notes, right? Okay, so if you listen to this and follow along, you will know that actually how these discrete pitches have been arranged to give rise to what we hear as a tune. Okay, so each of these is actually a tone of the type that we first saw, like the ship horn. It has a pitch associated with it. It also has a timbre associated with it because of the amplitudes of the harmonics that we chose, right? And we chose those amplitudes in a way that gave it this kind of fluty timbre, and that's why it sounded to us like a flute, right? Now, each of those notes was, the notes themselves of different pitches were arranged and they gave rise to a tune, okay? So when we talk about music, we use terms such as melody, rhythm, harmony. So the melody is essentially the pitch content. That is a sequence of pitches turns into a tune or the melody. Rhythm is a timing information, right? So music is also governed by an underlying grid in terms of you have an underlying pulse and the notes are aligned with that grid. And it turns out that if we can do an analysis of the signal to recover all of those acoustic signal measurements that give rise or underlie this tune. Okay, now why do different instruments produce different tones? Now we are going back to this, the sound production mechanism. A guitar, for example, has a resonating body. It has a number of strings. The strings of the guitar we already saw. Plucking a particular string of a particular length gives rise to a sound of a particular pitch. But when that sound interacts with the body of the guitar, certain of those components become amplified and some of those components become attenuated, and eventually we get a spectral envelope, the red line shown here, which gives it the very peculiar timbre of a guitar. Okay? So when that string sound, the sound produced by a string pretty much produces all the harmonics like we saw, but some of those harmonics get amplified more than others when they interact with the body of the guitar, which actually serves to strengthen the sound, but not uniformly across all frequencies, right? It tends to make some frequencies very high, some components high and some components low. And eventually we get something like, we still have the same frequency components with the same pitch, but the sensation that it generates, the timbre of the sound is, peculiar to what we have understood or remember as a guitar sound. Coming to, let's say, the human voice. The human voice, of course, you can sing and produce music, but even when we speak, we produce periodic sounds. And the reason we produce periodic sounds is because we have the vocal cords in the throat that vibrate, right? And it's a vibration of the vocal cords that gives rise to, that's the vibrating mechanism that gives rise to sounds. But with the human voice, we can produce a very large variety of sounds, right? We can change the pitch of our sound, but we can also make different sounds such as A, E, O, B, P, and so on. And those come because we have much more control than simply vibrating our vocal cords, okay? So for example, the sounds actually pass from the vocal cords to the outside of the lips. And in the course of passing, they pass through this very complicated shaped tube, which is the throat and the mouth. And we can change the position of our tongue and open our mouth wider or make it more narrow to change the nature of the sound. So I can have an A with a wide open mouth, or E with a much more narrow constriction of the mouth, all with the same vocal cord vibration And what I am doing is changing the timbre of the sound, that is by making it pass through the resonant chamber of the throat and the mouth, changing the relative amplitudes of those harmonics. Okay? So that's what we do. So that's essentially how we produce sounds of different pitch and different timbre. Okay, so this is just a cartoon that shows that you get different resonances because of the vocal tract changing shape depending on whether you make it narrow or broad or wide and where you place your tongue. So we can shape it in very complicated ways, and that changes the resonances of the tube, which eventually influence the timbre of the sound that we perceive. So for example, A and E, if you produce A and E at the same pitch, what you're really going to see is a lot of harmonics. This happens to be a 100 hertz sound, and that's why I'm seeing components at 100, 200, 300, 400, 500, and so on, right? But how is R different from E? I can see that the relative amplitudes, right? Which of those components is the highest, which components are very low, is actually different between the R and E, and that's why they sound different to each other, right? But the fact is that since they have the same components in terms of the frequency locations, we can produce these sounds to have the same pitch. Okay, so we just talk a little bit about hearing because that's also a very fascinating topic. And you know, everything we've seen about the decomposition of sound by Fourier analysis is exactly how our auditory system also processes sounds. So we hear a very wide range of sounds. You've already read this in your school textbooks that the range of frequencies we perceive are from 20 hertz to 20 kilohertz. And we also have a rather large amplitude range, you know, of close to 100 dB. And, you know, and just to tell you the order of between the softest and the loudest sounds that you hear. And when we listen to sounds, we can actually talk about their pitch, of course, and their timbre and their loudness. And the way these relate to the physical parameters of the sound that we saw earlier are in terms of the loudness is related to the amplitudes. If I increase amplitudes, we increase the intensity of the sound and therefore the perceived loudness of the sound. If I change the fundamental frequency, that is where the components are placed, we change the pitch. And if we change their spectrum shape, we end up changing the timbre of the sound. So what we are saying is that the Fourier analysis actually allows us to get to these individual attributes by which we perceive sounds, right? So by doing a Fourier analysis, rather than looking at the waveform, I can immediately relate, you know, what are those acoustic parameters that give rise to that particular sensation of pitch and the timbre. Okay, so what happens in our hearing? In our hearing also we have pretty much the ear, our external ear. Actually, our external ear, there's a ear canal, and then we have a eardrum. And in the eardrum, vibrations are the auditory pattern that is decoded by the auditory system beyond the eardrum. And finally, the pattern is synthesized and recognized in the brain, right? So this is something that you're probably familiar with, how the sound travels, impacts the eardrum, and then goes on to, you know, excite this fluid in the cochlea. And eventually that is the sound, that pattern is conveyed to the auditory nerve. Okay, so this is just a blow up of the cochlea. Okay, so what is it that gives rise to the sensation of pitch and timbre? So the cochlea itself is a very sophisticated mechanism. It's a coiled tube and its properties change along its length so that different regions of the cochlea have different resonances, natural frequencies of vibration. So as the sound wave travels through the fluid in the cochlea, it kind of gets decomposed into its components because different components excite different places in the cochlea. Okay? So just in the process of getting from the eardrum to the auditory nerve, the sound or the waveform has been decomposed into its components, pretty much like Fourier analysis. Okay? So in fact, the cochlea is called the ears Fourier analyzer because it's exactly this decomposition of the sound and giving rise to a pattern that is now spread out across the entire cochlea, which is then taken as a pattern and conveyed to the brain, right? So there are different nerve cells at different locations of the cochlea which sense the vibration at that location, correct? And then all of those get combined into the auditory nerve and the brain actually makes sense of the pattern. And the pattern is the pattern of these different frequency components, their locations and their amplitudes. Okay, so please stop me if you have any quick questions. Okay, so this is a cartoon that shows how high frequencies excite one end of the cochlea and low frequencies another, and how all of that translates into different auditory nerves getting excited depending on where they are connected to in the cochlea, and the whole bundle of nerves is what reaches the brain and allows us to make sense of the sound in terms of its pitch, timbre, and loudness. Okay, and now talking about how, there were some extremely, fantastic experiments that led to this understanding of the cochlea. So von Beckersey, for example, was, someone who experimentally showed by shining light through large mammalian cochlea, such as an elephant's cochlea, that indeed the vibrations that travel through the cochlear fluid do excite different portions of the basilar membrane, that is the membrane that lining the, lining the cochlea. And eventually there are, our understanding of hearing now has of course evolved considerably. And we're able to tell that the pitch is because of the positions that are excited in the cochlea. The entire distribution contributes the timbre, and the entire activity in the cochlea translates to the loudness of sound. Okay, so I have, some more explanations for, some more understanding of music that came about with, these kind of empirical experiments, which later were tied also to our understanding of hearing, and, explain a lot about what we call music and what we term as, proper combinations of sounds to make music. So it turns out that some of the earliest experiments in terms of, just observing the vibrations of strings and also of playing different strings which have different fundamental frequencies together are attributed to Pythagoras, who observed that two strings of different lengths typically played together gave rise to an unpleasant sensation unless the string lengths were in certain ratios. Okay, were in ratios in particular of small integers. So here is an example of a ratio that is a double ratio, that I have a particular fundamental frequency and I have twice the fundamental frequency that you see here. And if these are played together, they sound, very pleasing. I'll just move on to, some more examples to explain that altogether. Some of this understanding actually came about from the work of Helmholtz, who tried to relate this sensation of pleasantness and unpleasantness to the properties of hearing. Because finally, when we are labeling something as consonant or pleasing, it's actually based on what we hear. Okay, so if you consider this, we are looking at some examples here where we have one tone of a particular fundamental frequency shown by the blue lines, right? So it has components at 150, 300, 450, and so on, which makes it a 150 hertz tone. And you have a second tone with twice the fundamental frequency, right, at 300, 600, and so on. So if we play these together, so I'll play one after the other and the two together, and we'll see that it gives rise to a quite a pleasant sensation. And we have the similar feeling when we play them in the ratio of 3:2. As you can see here, the way they are placed, the fundamental frequency of one of them is 3/2 times the other. Okay, so it wasn't as blended as the first one, right? Because we can see over here that we have a lot of locations which were not covered by the first tone. But now we take a much higher ratio, not a small ratio, and listen to the tones together. So did you feel that there was a certain roughness in the last one? Okay, so that is called a dissonant, and that arises because of the particular relationships between these two sets of harmonics. So what is different about this is we have a lot of tones of these two components, some of which are very close together. And when you have two signs very close to each other and you superpose them, you get what are known as beats, right? And beats is the sensation that we hear that we term as roughness. So this is the beating phenomenon. So the beating phenomenon occurs when the signs are sufficiently close to each other, because on the basilar, in the cochlea, all of these are spread out, and the ones which are close are actually in more or less the same location, and they're giving rise to beats, and that is the sensation of roughness that we perceive. Okay? So this is one of the reasons, or in fact the prime reason why in music we have discrete notes. We choose a set of values or set of pitches or a set of notes, all of which are in ratios that typically when sounded together by and large would sound pleasing. Okay? We don't choose pitches that are extremely close to each other because that would give rise to sensations of beating like this and sensation of roughness. So this is about the construction of the musical scale, which exploits these properties of hearing, that the ear is sensitive to ratios, and the preferred musical intervals are those which are like 3/2, for example, or 2/1, or 5/4, and so on. And that's what we see in terms of the arrangement of pitches on the musical scale. They are chosen to be such that it doesn't matter which fundamental frequency you first pick, but all the remaining notes are in terms of simple ratios to that first note. Okay? And a doubling of frequency is called an octave. Okay? So all of these principles, both in terms of the breaking down of the sound into its components, as well as how our auditory system also actually perceives sounds in terms of the components, and also the interaction between two different sounds, once again in terms of the components of each sound. Okay, so now if we have to actually do Fourier analysis, there's something we need to keep in mind, and that is that we are actually going to be looking for these frequency components over long pieces of music, which actually have changing notes. So the Fourier analysis has to be done in small chunks, correct? So we need to divide a long musical signal into small chunks and subject each of that to Fourier analysis in order to determine its components. And from those components, we can talk about the pitch as well as the timbre of the sound, right? So that gives rise to a representation that is called a spectrogram, by which is meant that we take small regions of the signal. So what does this show? This shows you a signal which is actually changing in frequency, right? It is low frequency at first, and then I have a different note coming along with a higher frequency, and finally, much later, I have a note of a higher frequency. And if I was to analyze this signal, then I need to do a Fourier decomposition of small regions of the signal, because then that will tell me what the components are at any particular time, okay? And then I can actually show it by what we call a spectrogram, which ends up showing us that there is a component of this low value for the first 300 milliseconds, and then I have another component after that and a third component. So this is one picture which shows us the complete analysis of the signal, and the way we do it is by implementing this Fourier decomposition over small sections of the signal. Okay, so this is how it is done in practice. So if we were to apply that to our flute signal, for example, we would see something like this, because any given note has a number of components. Like you can see vertically, we have all the different components of the signal, and horizontally, we have the different notes coming along, right? So this orange line here or yellow line here actually shows the pitches, or how the components go up and down. So I just play this together, and what you need to observe is how the pitch is changing and how it is reflected in this Fourier transform that we are doing across the signal, or the Fourier series of each small section of the signal, which is telling us what the pitch is at any particular time. Okay, so here we show how this kind of applying this mathematical analysis to the signal actually brings out for us the whole series of notes. Now, in principle, you could put these notes down in terms of symbols and recover the melody in a written form. Okay, and now when we look at more complex signals, So we see that music does not typically comprise just one signal. We usually have, if it's a singing voice, you always have some sort of accompaniment with the singing voice. So there's a lot of instruments. So if you were going to look at this spectrogram representation of a piece of, let's say, a song, a recorded song, or a song in a concert, you would see a very crowded picture because there are so many different instruments interacting. Okay? So we can just listen to this and you will see, for example, that it is a voice and it's also accompanied by a lot of different instruments. So you heard a lot of different instruments. Can you identify some of the instruments you heard? You of course heard a singing voice, right? Yeah, the tabla was very prominent. And what else? Were there any other instruments? Yeah, the tanpura was there. It's always there in classical singing concerts. A harmonium was also there, right? Okay, but there was something about the singing voice and you could hear its pitch was varying a lot, right? And that's Indian classical music is characterized by that. So if we were to apply Fourier analysis to this, what you see, all the dark bands are all the different harmonics of the different instruments that were playing, okay, including the voice. Can you tell me where the voice harmonics are, where something is moving a lot? Right, the very dark portions where you have a lot of movement, that's where the voice is. But if you were to do a Fourier analysis and find all those sinusoidal components and then group them together in terms of the different harmonic series and then identify which one was the voice, then you would see this. Okay, so the way we are looking at this is the yellow line is showing us how the pitch, it's only showing us the portions where the voice is present and it is tracking the pitch of the voice. Okay, and this is an outcome of an analysis where you first identify all the sinusoidal components and then group them together and then have some other means of knowing which one might be the voice and isolating that. And in principle, you can reconstruct only the voice by just taking out the set of harmonics which correspond to the vocal pitch. Okay? So that is how we would do that. And of course, now this opens up a lot of things. For example, we could study this and find out, for example, what kind of music this is, what is the style of singing, right? From the way the pitch is varying. We could also tell what would be interesting to a music listener about this singing. They would like to know, for example, who is singing. They might want to know also the raga that is being sung, right? And the raga refers to the scale. And how would we tell that, for example? What distinguishes one raga from another? The notes, right? So the notes are distinct. The set of notes that is utilized by a particular raga typically is different. Not to say there are ragas that have similar notes, because there are other distinctions also. But at the first glance, you can sort of group ragas together just based on the notes that are allowed in the ragas, right? So that is something we could make out if we measure these pitches and then we put it back on our original scale and found out where those pitches lie, we could do that. So I'll just show you an example of that after this. We can also see patterns where repetition occurs, right? So now I'll play this for you again, and when you listen, you'll see that what I put in the box is actually the same little tune or piece of singing that is coming back. So the Guru Bina Gyan, that refrain, it came back at the end, and that actually is obvious to us also from the same patterning of the pitches, right? So we can use this analysis also to identify similar regions and maybe identify, for example, the chorus of a song, correct? So you had this very complicated signal which we now reduced to just capturing the vocal pitch variation, and that is already telling us a lot about, where similar portions occur, for example, right? Okay, we won't talk about time because we'll run. So I'll just straight away get to the applications. So what are the different things you can do with this analysis, right? music recommendation tagging. By tagging is meant you can label a piece of music by a particular style or a particular singer. I mean, there are so many kinds of tags that people give, right, to music. And that can be used for music recommendation, right? So if you use some of these services like Spotify and so on, they use a lot of tags to determine, what kind of music somebody is consuming, and then try to find similar music with similar tags to serve up to them the next time. Music appreciation just by the kind of understanding that we can get, of a particular style and so on from this kind of a study. Searching for music in terms of finding, let us say, similar music on some attribute or the other. And of course, we can give feedback to learners, right? You could analyze somebody singing and compare it with what is supposed to be sung. For example, if you typically, the first attribute of a good singer is that they sing in tune or they sing the correct pitches. And that's something that we could measure by doing this kind of analysis and comparing how close they are to the reference, right? Okay, so talking about tagging, one of those important tagging is what is called genre recognition. So all of these are different, types of music. And one of the main thing that the instrumentation tends to differ. Of course, there are other attributes that differ also, like the tempo might differ and so on. But all of that lies in the sound signal or in the music signal in terms of the spectral envelope. So the timbre of how it sounds like, for example, is a good signature of the particular genre that it belongs to. Okay, so you could look at the timbre by doing this kind of signal analysis, the Fourier analysis, and determine how the energy is distributed across the different frequencies, and that would be a good indicator of the category of that music, in this case the genre of the music. We already talked about this. Okay, so now I'll just entertain you with one example. So I'm going to play a pair of music clips, and then you have to tell me if they are the same or different, and if they are different, on what axis or what discriminates them, musically speaking, and how would we recover that distinction automatically by doing the analysis, the Fourier analysis.
पहला नशा पहला खुमार.
Okay, so was that the same clip or a different clip? Okay, what else? Did you find one of them better to listen to than the second one? Okay, yes, there was a loudness change, but if you think about it, it also seemed like it came from a more high quality audio system, right? It had more low and high frequency components. Okay, so we call it the presence. So the other one was recorded with using a very simple recorder on a mobile phone, the original song being played out, but recorded on, using something that was not able to capture the entire spectrum of the signal and just knocked off. Something like if I was playing something and transmitting it over a telephone line, the very low frequency would get cut and the high frequencies would also get cut, right? So the timbre changed. So if we were to look at the analysis of these two, we would actually see that they are the same music, but they have been processed differently. One is being played out through some very high fidelity speakers, and another one from a recorded form which has lost many of its components. Okay, so it is just a kind of a degraded version, right? But it's the same song. Okay, let's see this. They were different, right? What was it about the second one that was different? The beat was faster, right? So the tempo was faster. It was basically the same song, but this is what we would call a cover version, right? So it's been redone by someone. They're trying to sing the same song, but then of course it's the basic pulse. It's the same tune. It's the same lyrics, the same orchestration, but the tempo is faster, right? So this is also something. So how would the spectrogram of this, if you were to do the analysis of the piece, be different from the spectrogram of the other? Correct. The spectrum would be compressed in time. It would look the same at every instant. You would be able to find a matching portion, right? So in the vertical sense, you would have all those details, except they would come more rapidly in the second one, right? So you could still compare patterns and determine whether it's a cover version or not. Some of these things become important even in copyright issues and all that, right? So all that I'm trying to say is that we have this way of computing or doing this mathematical analysis and recovering a pattern which tells us so much about the music that we are able to tell only by our listening. Right? Okay, now listen. So we,
நாணம் என்னும் இலக்கணமில்லை ஆசைகள் அது ஃப்ரீ பாவை என்றும் சுதந்திர பறவை காவல் தேவையோ.
So what was that? Completely different song, right? Was there any similarity? Right, the melody was the same, right? So this is from the late 70s, I think a Bonnie M song, and that got into a Tamil movie a few years later. So it's completely different in terms of the artist, the production, the instrumentation, everything. But there's something about it that if you lay a finger on it, you'll say that the tune has been borrowed, right? So how would we tell if we did this kind of, what kind of analysis would we have to do to establish? You remember that controversy with the Kantara movie, right? That was actually, it's another level of this, but I'll get to that. But it turns out to be quite important, right, to establish these. So how would we do, what kind of analysis would we use? I mean, what would you see if you did the spectrograms of these two that you could, bring out in order to determine how similar these are? They're going to look completely different, right? Because just everything is different about the signal and what we are hearing, but that attribute which is the same, which we are calling like possibly a borrowed tune, how would that come out? So you remember that example I played earlier with the Bhimsen Joshi song where we saw those pitch traces of the vocalist. So if we did that kind of analysis and only recovered or reconstructed only the varying pitch of the vocalist in the two, we would begin to see some patterns, like the arrangement or the trajectory or the movement of the pitches in portions would come out to be similar, right? And that's why we get a feeling that the melody is matching, okay? Okay, so then we would kind of maybe dismiss this as same tune. Of course, now there are many such, we are moving from one end of the arrow to the other. Oh, it's almost time, I'm going to stop now. By actually relaxing the similarity, right? First we had the same song, then we had a cover version, a little relaxed version, same tune, oh, completely different song, but snatches of the tune are similar. Then we could always talk, okay, raga, the set of notes being used is the same, right? So that's what happened in Kantara. I think people said, oh, it's not the same tune, but they're referring to the same background, tonal material, or the same set of notes. Same scale, the same genre, everything falling under, let's say, Indian classical music, for example, would be same genre, or particularly Hindustani or Carnatic. So there are many applications for this kind of analysis. So I really don't have time to go through this, but we can actually detect differences in style by looking at variations in the pitch contour. So this is an example of a discriminating a Hindustani ala from a Carnatic ala, which is a lot more florid and ornamental simply by extracting this fundamental frequency variation. And finally, if we wanted to find the underlying notes, then we would take the variation of pitch and we would count all those pitches and make what we call a distribution. And then the distribution will tell us which notes are being used. So as you are singing, the pitches are moving, but if you were to collect all of this and plot them in a histogram or a distribution, then you would know the note location, and that would allow you to establish, for example, if two songs are in the same scale or the same raga. Okay, fine. So to summarize, what I ran through is fairly complex material, but I just tried to bring it out through examples. just to give you the main idea. All of this actually has to be developed, fairly elaborately to make complete sense. So don't worry about that. So the main points were music is mostly periodic signals. And the perceptual character, which I mean is, the attributes that we hear when we talk about, let's say, tune, high pitch, low pitch, or, a voice like somebody's, or a style like Carnatic music, and so on. We are referring to what we perceive. And it turns out that all these perceived characteristics can actually be obtained by computing the Fourier spectrum. Okay, so we often just call it spectrum analysis, but actually it is the Fourier analysis that we are doing. And when we are looking at the components that are present in the signal, what their amplitudes and frequencies are, that's what we call the spectrum analysis, right? So from that spectrum analysis, we can tell a lot about the attributes, and therefore we can do what is called machine listening. Just as humans listen, we can have machines that listen and decode sounds and maybe become more intelligent in terms of, let's say, finding the music we like, or identifying whether it's a case of musical piracy and so on, right? So we are able to compute because we begin to understand, or we're able to see these connections between what we perceive and what we can compute on the spectrum, through the spectrum. So machine listening models actually are based on these Fourier decomposition principles. And also this Fourier decomposition is what our human auditory system utilizes, right? So we saw that it's pretty much a separation of frequency that takes place immediately after the eardrum. So it's not even something happening deep in the brain. It's happening in a very physiologically tangible manner right at the eardrum, just behind the eardrum. So that's a very sort of fascinating state of affairs. And of course, all these attributes that we were computing, they have multiple applications. We can even synthesize new sounds, because now we know to change a sound, what do you have to do? Even if it has the same pitch, I can still change the quality of the sound by changing the amplitudes of the harmonics, right? So it's going to give you a different sound. That's what we saw in some of the examples. So synthesis of sounds is also a big area where you're trying to, design new sounds to go with some particular, maybe some particular visual scenario or something. For example, there are entire projects on how to generate sounds that can be used in a hospital, different kinds of alarms, for example, right? They should be sufficiently related to what you are measuring, like something about the heart should, give you a sense of, okay, something is going wrong with the heart, so it should be that kind of a sound, and so on. So sound design and relating to it, what you are trying to, represent is quite important. And once we know what we want to do, we know that our understanding of how the signal is constructed is going to be really useful in actually implementing that type of synthesis, right? And of course, you can do a lot of research on music. Like we said, you can do a lot of scientific analysis of music. How has our music evolved over the years historically, for example? How did different singers evolve? How was something passed down through the generation? By doing all this kind of analysis and looking for those differences. Much as musicologists who study music analytically do a lot of listening, now you can actually do it on much larger data by using computing and then finding out similarities, differences, systematic changes. So there's a lot of possibility for empirical work. Okay, I'll stop here. Thanks for your patience. Yeah, I'm sorry if I had to run through some of the more complicated this thing, but even if you got some snatches of it, I think. Okay, yeah, so that's a good question, because supposing, yeah, so this actually has applications beyond music, of course. For example, in noise reduction, right? So you have something that is coming to you which is mixed with a lot of background noise. Let's say a human speaker, and then so you have this human voice, but you also have a lot of background noise which you want to bring out. So again, the spectrum is going to allow you to do that much better. See, if you just take that, it's going to be a completely complicated signal, right? The signal and the noise and so on, it's all completely mixed when it is a function of time, correct? But if I want to unmix this, I can do it if I do a Fourier analysis or a Fourier transform. And why does it improve my chances of unmixing it? Because now I'm going to spread it out on a two-dimensional plane where this is time and this is the frequency axis, right? And then I have better chances that in this plane, I will have non-overlapping components, right? For example, if there are two speakers speaking, a male and a female, with different pitches, then the male voice is going to have harmonics at certain frequencies, and the female voice might have higher frequencies, and they may not overlap, right? So F0 of the female will be here, 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 F0 to F0, by F0 I mean fundamental frequency, and the male voice might have fundamental frequency is lower, and the multiples of the fundamental frequencies are different places. So while they were completely superposed here I'm going to have two sets of harmonics, right? And then I can use some other understanding. For example, my understanding is a female pitch range is always between, let's say, 200 and 300 hertz. The male pitch range, let me consider to be non-overlapping, between 100 and 200. Then I know when I find these things, how to group them together, and I will be able to tell which is the female voice because I'm bringing my other knowledge of where I expect the female voice components to lie. Okay, so that's how I would separate that. In the case of what you mentioned, the signal degradation, most common like fan noise or, they are also periodic. If a fan is rotating at a certain speed, it's going to give you strong, periodic lines, harmonics here, which would be completely mixed in the waveform, but you can actually remove them by just zeroing out these parts and then converting this back into a time domain clean signal. Correct. Exactly. Right. So they have something like converting it to an input representation, in which this becomes possible, separation becomes possible. And that input representation is some type of time frequency representation obtained from the Fourier transform. Every curve out there. By that you mean? Every function. Right. See, every function. The premise of being able to separate them, we should have them be mostly non-overlapping. Okay. Now, that's not guaranteed. There could be some kinds of noise which is actually overlapping some of the signal components, right? In that case, we would have some loss of the signal in the course of this thing. In the course of trying to remove the noise, we would lose some of the signal. So your separation would not be that perfect. Okay. So these are indeed the patterns that I use. And these days, of course, there's a lot of deep networks, and you must have heard of deep learning, that is applied. And they pretty much it still uses this principle, but they just do some more sophisticated separation by showing the network a lot of examples of what the combinations look like, so that the network is able to minimize the loss by having a really good idea of what exactly to suppress in this. But indeed, the representation that is used is something that essentially separates out frequencies at every time instant. Okay, fine. So the auto-tune actually was, so you know what the auto-tune does, right? Essentially, if you have a singer and you finish doing a recording and then you feel that some parts are a little out of bass-sur, a little off, then you can go in and actually fix them by, picking up those harmonics and just shifting them around. So in this image, you had somebody singing here and you wanted to shift them, then there's a way to get all the harmonics corresponding to them and shift them all slightly mathematically, okay, by a certain ratio so that they get to the correct place. Now, the auto-tune turned out to be also another style of singing, right? Because when we normally sing, what happens, the voice tends to quiver, right? Like we saw. Of course, that was a very good singer whose voice was quivering, but your voice naturally quivers. But auto-tune is a way of changing it into a piecewise flat kind of singing, right? So you take each quivery portion and replace it by the nearest piano note that it is supposed to have, and it gets that auto-tune kind of character. So that turned out to be a style of singing where indeed to do these kind of modifications, you have to decompose it using these components, Fourier components, and then manipulate each of them so that eventually you get the desired pitch. So you move some component to another place so that that whole set of harmonics now has a different fundamental frequency. Okay, so if that is okay, then the next question was, so this music analysis actually, similar to what, Janvi was talking about, we have such a rich scholarly tradition of music, and Indian classical music, for example, is considered to be a very, it's called a classical tradition because it's very sophisticated theory, right? So there were a lot of old treatises written about the music that, about the rules that are followed, how ragas were constructed and so on. But there has not been a lot of empirical analysis. And when music is taught, it is usually taught by example, right? Teacher sings, you sing, teacher says, no, that's right, sing it again, and so on. It's not really taught always with a theoretical grounding. So it becomes quite interesting to analyze actually the music of, let's say, great singers, and then determine, whether they really are consistent with those so-called principles. And even so, the principles themselves are not very quantitative, right? So there are some, kind of generally accepted notions that in this raga, the notes are slightly higher, but it is never really written in the treatises, for example, how much higher, right? By how many, a unit of frequency. But that's something, if you go and you measure in actual performances, you come up with nice numbers. And the amazing thing is all those numbers are consistent across performers. So by this teaching tradition itself of learning from master to student to their next student and so on, they've actually sort of, implicitly acquired what that slightly higher means, although nobody has articulated it. And now we go and get to measure it, right? Because we can do all this and we can actually get to everything and measure it, right? So that's how you can build further on the theory and get a deeper understanding about the structure of music and, what are those commonalities and differences, how it's evolving, and so on. Okay, so that's just one example of. So there is this kind of, and especially in Western music, a lot of it is already written down. So a lot of people just analyze the written music, the written form, just like you would analyze text. But in Indian music, we don't have a written form that adheres. It's very skeletal. It does not really tell you everything about the sound. A lot of it is actually just from people's training that they manage to fill in. So these are some of the things that you can actually uncover by doing these kind of analysis.
And thank you, ma'am. Thanks for visualizing the sound for us.
Thank you. End of a long day for me.